We're recording. All right. So I guess we could start.
Okay.
Okay. So hi, friends. Thank you for joining us this evening. This is our first journal club of this semester, so that's cool. I don't have far too much to say. I really just want to hand it over to our man of the hour. So with that, thank you for sharing some of your wisdom this evening. So I'm excited to hear what
Let's
you have.
see. Let's see if we can call it wisdom. But yeah,
We will
I
see.
am
We will see.
happy. I am happy to be here and sharing this. So I ended up being here because I don't know if all of you know, but I was the 152 professor for Morgan, Kenya, and Edgar. And then Morgan encouraged me to do something that will kind of exact you a little bit more about physics, although I think everyone here is already interested in physics. But because of that, I decided I picked this old paper, ancient paper from 1982, because it is a paper very dear to me, even though I haven't read it until until this journal club. But I always kept hearing about it, and it was mentioned to me during my undergrad by one of my professors. The one he was my advisor in my undergrad thesis, and we were always talking about how this guy over here was so good at doing experiments for quantum mechanics, and I was just doing quantum optics, which is pretty much what he does here. But the main idea of this paper, the reason I also picked it, is because it deals with the fundamental interpretation of quantum mechanics. And that's what I find the most exciting. So I decided to pick something that was very exciting to me to see if I could make you excited about it as well. So let's see. So my idea is going, not, I will go a little bit over what the experiment is, but not in too much detail. What I want to do is I want to give you the context, historical context in a way, and a little bit of the, let's say, the conceptual intricacies and the properties of quantum mechanics that would allow us to understand this paper. Okay, so, and of course I will discuss the results on the paper and so on. But to do that, you know, just by reading at this, you need to know a couple of things. It says Einstein-Podolsky-Rosen-Böhm-Gedanken experiment. What is that? And what are Bell inequalities? So we're going to discuss what these are and why they are important. And to do that, I'm going to start with another experiment, which are the Stern-Gerlach experiments. This is a fundamental experiment in quantum mechanics, as I will try to explain. And this is it's also related to that professor I mentioned you. His name is Boris Angelo Rodriguez, if you care. But he was my professor in undergrad, and when I mentioned to him, well, actually, the first time I met him was as my professor of advanced classical mechanics. And then he was always telling us how quantum mechanics was even more exciting and so on. And then I started my first quantum mechanics class, and it was quite boring. Not extremely boring, but I was like, this is not as exciting as what I was doing in advanced mechanics with you. So he told me, oh yeah, it's normal because professors, I mean, the general idea is to teach this wave function, and you have these potentials, and then you find transmission probabilities, and it's not very exciting. But, and then he told me, why don't you get this book, which is called Modern Quantum Mechanics by J.J. Sakura. It's a classic, and you start reading from there, and then we can have discussions about the book. And then the book, this is like in the 4th page already, is doing this, which shows why quantum mechanics is so exceptional instead of going with this wave function thing. Of course, the wave function is important. I'm not saying it's not, but it doesn't show the fundamental, let's say, or the most interesting facts or consequences of quantum mechanics. So let's think about this experiment then. What we have here is an oven, and when what happens there is that atoms of silver start coming out a beam. You can collimate the beam, and you only get like a beam of atoms being shoot out from this oven from heating up the silver. So you get these silver atoms, and these silver atoms have, because of their electronic properties, they have one electron in the outer layer, and this electron has a spin 1/2, and that makes, because all of the other spins canceling out in the ground state, this atom as a whole has a spin 1/2. So what is a spin 1/2? It means that you can only have two values of the spin. You can only have it pointing up or pointing down in a given direction, right? Spin, for those of you that don't know, is intrinsic angular momentum. All of you have dealt with angular momentum, at least in classical physics. Well, spin is what is known as intrinsic angular momentum. And quantum mechanics, in particular, this experiment right here, when we start with the simplest version on the top, shows that this quantity is quantized. It means it can only have these two values, is 1/2 of h bar or minus 1/2 of h bar. That's it. So when you can place a non-uniform magnetic field in the z direction, and this is represented by this box here, it says Gerlac apparatus in the z direction. And what that does is the interaction of this spin of these atoms with this magnetic field divides the beam in two. So the particles that have spin plus positive, so plus c or plus 1/2 h bar, will go into this beam, but the ones that have negative h bar over 2 go into the bottom beam, right? The interaction with the magnetic field divides these two beams. And that is what tells you that there is only two possible values, because you only see two beams. Now, this is where the interesting thing is going to happen. If you measure this, the spin again by setting up another Stern-Gerlach, by you block the negative component, then after this one, you're only going to get one beam, which makes sense, right? If all of these are with the spin pointing up, then when it comes here, you expect here to see only spins pointing up, right? Nothing weird there. Well, before I move to the second, the other two setups, I want to mention something about quantum mechanics that Einstein didn't like, which goes in right here. So when these atoms come out of this oven, they come out with, this is representing the quantum state of these atoms, or at least of the spin of these atoms. That is equal to this superposition over here. So if you are not familiar with this notation, we're not going to do any calculations here, but I'm showing it just to so that I can speak a little bit about these quantum states. So this, when you write it like this is a way of representing the state phi of these atoms, right? It's just the quantum mechanical state. And in principle, if you know the quantum state of a system, you can find the probabilities to find any single value of any quantity you want, if you know the full state. So the state that comes out here is the linear combination of the spin pointing up and the spin pointing down, right? So these are just coefficients, right, for this linear combination. And what they represent is that if you take, they can be complex coefficients, because these vectors or these states live in a complex space, vector space, then this, if you take the absolute value squared or the amplitudes of these two coefficients squared, then those represent the probabilities of obtaining the given outcomes. So whatever value you have here, if you square it, I mean, if you square the absolute value, because this can be constant, then that represents the probability of the spin being pointing up. This beta is if you square it, you're going to get the probability of the spin pointing up. And because these are probabilities, they should add up to 1, right? So alpha squared plus beta squared has to be equal to 1. So what we have here is a state in which the spin of the actual spin of this atom is not determined. It doesn't really exist. And that's what Einstein didn't like. For him, a theory must be a realistic theory. I'm going to talk about what that means in a little bit. That means for him, the probability of finding something should be due. The reason that we have to do a statistical theory is because we don't have enough information. But quantum mechanics says that the nature of this system is probabilistic in nature. Therefore, that there is not something else that will create, there is no definition of the spin before it crosses this magnetic field that divides the spin into two. So until you measure, the spin is not determined. And Einstein didn't like that. Okay, for him, the quantity spin should be defined. An atom should have a definite spin. And he thought, well, the probabilities here that I see, it's because I don't have enough information of this system. Therefore, I need to come up with this probabilistic theory that is incomplete. Okay, so this is the part of when you read in the article, if you looked at it, that says realistic local theories, this is the realistic part. So realism says that things exist no matter if we look at them or not. For example, if a tree falls in the middle of a forest and nobody sees it, then someone like Einstein will say, the tree still fell. I don't care if nobody sees it, that tree fell. But other people might say that if nobody saw it, then it didn't happen. Okay? So in case of the tree, I agree with Einstein, but in this case, this is why quantum mechanics is so complicated. I disagree with Einstein. So I think that quantum mechanics is complete and that the probabilistic nature of it is fundamental. Therefore, the theory is complete. But this is what I believe, and this is kind of where this whole thing is going and where this experiment was trying to do. But let's continue here a little bit with these experiments. Now, let's see what happens if after blocking the negative component, the negative component of the spin, right, the one pointing down, if I block it and then I measure the spin in the x direction, which is perpendicular to z, right? If I do that, then I get equal probability of getting plus or minus, right? So it's spin pointing in the x direction or in the negative x direction. Okay, so already interesting. But the most interesting thing that quantum mechanics, and this is fundamentally quantum right here, is that if after you measure the x component of this, you block the negative x component, and then you measure the z component again, you again get from equal probability both positive and negative spin in the z component, which is weird because over here you block the negative component of the spin. So over here you're only entering with a state that has positive c, so it's this state, right, pointing up. Over here you're entering with this state, positive x, right? You measure the x, the spin in the x direction from the state that has the spin up. This one already has a defined spin. But if you block the negative one and you measure the z component again, you get that you also see a beam on the negative z direction. Super weird, right? Like that is definitely, it's like, imagine you have over here red and blue squares, right? And then here, what you do is you say, okay, I'm just going to stay with the squares. So now I have squares that are, instead of spheres and squares that are red and blue, I only have squares because I'm blocking all the spheres. I just take out all the squares, but now these squares are red and blue. So over here you say, okay, I only want the blue squares. Cool. So, and then you say, okay, supposedly over here, what is coming is only blue squares. But then you ask yourself, is this a square or is this a sphere? And then you go into this bag and now you found a sphere, even though you already took them all out. So definitely counterintuitive right there, right? So quantum mechanics shows us that this type of situation can occur in nature, right? These experiments have been done, and our minds can be a little bit troubled about this. That's why there's been so much, there was so much problem at the beginning of quantum theory, and that's one of the reasons why Einstein didn't like it. But now Einstein didn't like something even more complex than this, and that has to do with what is called quantum entanglement. So now we're going to talk about this Einstein, Podolsky, Rosenbaum, Gedanken experiment, and Bell's theorem. Okay, and here's where we start talking a little bit about this paper in particular. So in this case, what we have is this quantum state, but this quantum state is the state, let's imagine, 2 electrons, right? So this says for any direction n that I have this linear combination of a state where both of them are pointing in the positive n direction, plus when both of them are pointing in the negative direction. This factor of 1 over the square root here tells you that the probability of having this is 1/2 and the probability of having this is 1/2. Okay, so imagine this state. So this state is a quantum superposition, but you have 2 parts. It's a 2-part system, right? Now, what happens is the following, and this is what Einstein thought about in his first, first you have just Epr Paradox. This paper was written by Einstein, Podolsky, and Rosen in 1935 because Einstein didn't like quantum mechanics, and we will see why. Well, because quantum mechanics, which is described by this state over here, will say that if you measure if you measure the spin of the electron that comes in this direction, imagine the 2 electrons go in opposite directions and they're very far apart from each other. Imagine you measure the spin of the electron 1 over here. So if you measure the spin, and for now let's think that this is the direction in which you're measuring the spin. Let's imagine the case in which it's equal to n, the one that I'm showing here, and this is also equal to n. So if you do that, then you can have, if you using the Stern-Gerlach apparatus, you can have that this goes in one beam or in the other, right? The electron that goes to the left. Makes sense, right? It's the same experiment as above. So you have equal probability of having this outcome or this outcome. So point plus one means pointing up or in the positive n, and plus minus one means negative n. So if you do that, let's say you have one electron and it points up. Well, it turns out that what this state is telling you is that then the electron, the spin of the second electron has to also point up. And it doesn't matter what you do here. If you measure it, you're always going to get plus as well. If this one was plus, and you're always going to get minus over here if this one was minus. So you do something over here, and that affects something that is very far away, that in principle can be at a distance such that what that means is that a signal has to travel from here to here with a speed that is higher than the speed of light, right? So that's why this theory will be non-local, and it will violate special relativity because signals will have to travel faster than light. So that's why he didn't like this. Clearly, because he was, of course, very proud of his work with relativity, which is an awesome work, by the way. So, so then what he did is he came out to this with this experiment. He said, "See, this doesn't make sense. This will imply that that this theory is not only not realistic but also not local." So he said that quantum mechanics was an incomplete theory in that seminal paper. In reality, that paper didn't think about this experiment exactly, but an experiment thinking about the position and the momentum of two different particles. But then later, in 1952, Bohm, that's where the B comes here, came out with this experiment. And he said this experiment is equivalent, and he tried to prove. He came up with this theory called the hidden variable theory that says that this can be explained with classical mechanics if we think that we don't know there are some variables that we don't know about, or some information that these two particles, when they come apart, already share, and that's why the measurements are completely correlated. So he said, quantum mechanics is incomplete, it's just we don't have enough information. That's why it looks like this action at a distance occurs. So there was a lot of discussion there. There was the defendant of quantum theory being complete in those times was Bohr. But then later, in 1964, it was Bell that came out with an idea. He was in agreement with Einstein. So he said, okay, this is just a bunch of, it was just more like a philosophical discussion, that something that could be done with experiment. And then Bell said, okay, well, I'm gonna come up with a quantity, right? This is what Bell theorem is. And he said, there's a quantity that can be measured, right? Thinking about this experiment, and we're going to define the quantity later. But he said, if you use a classical theory with hidden variables, then this quantity has to be smaller or equal to 2. In reality, I am lying a little bit. It was a different quantity. This was a quantity that it was come up by 4 scientists, and these are the initials is Clauser, Horn, Shimony, and Holt. I'm gonna send you the links of all these papers at the end, but it's basically the same idea. But just these 4 scientists came up with something that was better to do with that was easily measured. Bell's quantity was could be measured, but it was not as easy, basically. But the idea is that there's a quantity that you can measure, and this quantity, if we have a realistic local theory, then that quantity in absolute value should be smaller or equal than 2. If but, and then he said, and I mean, I believe in realistic local theories. It sounds like the logical thing to do. So then that means that if quantum mechanics violates this, then quantum mechanics is wrong, right? So that was his argument. And he said, he proved that for quantum, that if you do quantum mechanics, then this quantity in absolute value could be bigger than 2. Right? Let's remove the equality sign. So he proved this for this experiment, and he said, okay, quantum mechanics is wrong. See, I'm showing you. But experimentalists were like, you're just giving us a chance to prove you wrong, right? So so that's where this paper comes along, right? This paper, there were a bunch of experiments before this paper. So this was in Bell's theorem was in the 60s, and then in 1970 is when this new setup, I will define it soon, don't worry about it, they came up with this setup that was better for experiments, right? Giving experiment, they were not experimentalists, but they told experimentalists, here, do this, and then we can see what's going on here, right? Decide on one of these two theories. And experiments started to happen, and quantum mechanics predicted that this was bigger. Experiment was predicting that it was also bigger than 2. But the experiments had a lot of flaws, and this experiment that we're going to talk about was the first that started to be very credible, okay? So in this particular experiment, I'm going to talk a little bit about the experiment. What we have is not 2 electrons, but we have 2 photons. Instead of electrons, we have photons, right? These photons are the result of an interaction of calcium atoms with 2 nonlinear lasers, right? So they were so good, these experimentalists, that they could create this state, this quantum state, with 2 lasers at fixed frequencies, and there were like pulse lasers, not continuous lasers. So they could excite these atoms in such a way that they will emit 2 photons like this in opposite directions. They have to be emitted in opposite directions to conserve the linear momentum, but whatever, that's not important right now, but they will be emitted like this. These 2 photons will have different wavelengths. But the interesting thing is that they will be in this entangled quantum state of polarization. So instead of spin, what they were measuring was the polarization of this photon. So if you remember what polarization is, or if you don't know, it's just basically the direction of the electric field. Photons are basically what make up the electromagnetic wave, the electromagnetic field, right? So if we talk about electromagnetic waves being polarized in a direction, we say the electric field is directed along a given direction when it's linearly polarized. So in the case of photons, what we have is 2 perpendicular directions. So if you have n plus, it means the polarization is along this direction, right? If you have n minus, it means the polarization is perpendicular to that direction, okay? So what they were able to create is 2 photons that were entangled in this way. So whenever you have polarization in this direction for one, the other one is also in this direction. If you have this direction for one, the other one is also in this direction, okay? That's what it is. Now, Let me connect my iPad. I forgot. I have it here though, so it's not a big deal. So this is kind of the scheme that they use. Instead of electrons or atoms, they decided to use photons, which have a couple advantages. One is you can use optical fibers to make the photons travel very large distances, for example. Now, I'm going to try to define, I'm not going to try, hopefully I'll succeed, to define this variable S. So let's talk about this quantum state and what is known as the correlation function. So remember, we have two photons now, or two electrons, whatever. Sometimes I will talk of them indistinguishably, but they are different. They end up having a similar quantum state. So the idea is the same, even if you have spin one half particles or photons. Now, I'm going to define the correlation function, and this correlation function depends on A and B, which are the direction in which I'm going to measure the polarization of these photons. So instead of making A equal to N and B equal to N, I'm going to use two different directions, right? And they can be, the relationship to N is not important. So you can, for example, in one side over here, what you do is you measure, let's say A goes in this direction. So you're going to measure if the photon has a polarization parallel to this or perpendicular to this, right? And on the other side, you can have another direction, maybe this one, doesn't matter, right? You pick another one and you measure the same, if it's along that direction or perpendicular to it, okay? That's what the plus or minus means, parallel or perpendicular. So if you do that, then the correlation function is going to end up being defined by this. And I will try to convince you why this is the correlation function and what it implies. So it's going to be the probability, and these are joint probabilities, of obtaining plus. That means you obtain that the polarization is in the direction of A for photon 1 and in the direction of B for photon 2, or you obtain that minus, which is that the polarization is perpendicular to A for photon 1 and perpendicular to B and photon 2. And then from that, you subtract the polarization, the probabilities when you have parallel and perpendicular on each of them. So this one is the probability of obtaining a polarization parallel to A for photon 1 and perpendicular to B for photon 2. And this is parallel, the minus means, perpendicular to A, plus means parallel with respect to B, right? So why is this the correlation function? As I'm not going to prove this, but this is going to end up being between these values. It's going to be in absolute value smaller than 1. So it's very nice. And if you look at our state over here, just looking in terms of n, let's assume A and B are n, you see that plus is equal to 1/2 and P minus is equal to 1/2, right? The probability that they're both parallel or that they are both perpendicular is equal to 1/2, because you have to square this over here, and the probability of these ones is 0. You cannot obtain parallel in one and perpendicular on the other with this quantum state. So this state, as I said before, is completely correlated, because when you measure here +1, you already know that over here you measure +1, right? So the measurements are completely correlated. And this, if you put it in this equation right here, gives you exactly 1. So then we see how this equation really characterizes, which is the maximum value of this, and that state is maximally correlated, right? So we see how this describes that situation. And the other limit that is interesting is 0. Imagine you have the same probability of obtaining all of the outcomes, right? So basically, if you measure here, that is plus, if all of them have the same probability, then you will have the same probability of obtaining plus or minus over here, right? In that case, there will not be correlation. It doesn't matter that you get plus of here or minus here, you still have the same probability of obtaining plus or minus over here. That's the case when all of these are equal to 1/4, when all the probabilities are the same. That will be when there is no correlation. In that case, then you see how, I wrote it over here, but you see that in that case, you get equal to 0. This is the case that I was mentioning up here, but you see that if there is no correlation, this function is equal to 0, which is the case where all the probabilities are equal. That indicates no correlation between these measurements. So this, using quantum mechanics, for this state over here that I wrote, and this I'm not going to prove, that's not the point over here, but you can calculate that specifically. You can calculate all these probabilities using quantum mechanics, and you get that this correlation function I'm too used to writing electric fields and I put a vector there. So this is the correlation function of when you measure in the directions A and B, and that using quantum mechanics and the specific state, so maybe it's even better to put that this is for the state shown above, V, for that is equal to cosine of 2 times the angle between these two vectors or the two directions, right? So you can prove that, but the proof is not important. I just want the important thing here is that quantum mechanics predicts a value for this. It's not that quantum mechanics cannot calculate this. It predicts a value and it's equal to this, which is clearly between -1 and 1, right? Because the cosine is between -1 and 1. So you can calculate it with this for this particular state in which these photons are. Now, the quantity S that we were talking about in Bell's inequality is defined by this. So it's not an intuitive definition, but it is a sum, a linear combination, because we have this negative sign here, of different correlation functions for different directions. So what you do is you do the experiment using directions A and B, and you find that correlation function, right? Then you repeat the experiment, but you change the direction of B for a new direction, B prime, right? You just rotate that direction. You change it. And then you find that new correlation function. You're going to subtract that one from the original one. And then you do the experiment again, but instead of changing B, you change A. And then you change both. And you add all of those together. So if you these correlation functions can be calculated using classical theories or quantum mechanics. Okay? How do you do that? Because these probabilities depend on the theory that you use. If you use classical theories with hidden variables, you find some values for these probabilities. If you use quantum mechanics, you find other values. So if you use classical hidden variable theaters that are local and realistic, then you get that this S has to always be between -2 and 2. That's what this theorem says, right? And it was proven So first, not for this particular quantity, it was proven by Bell, it was for a different quantity, but then this, for this particular quantity, this inequality was proven by Clauser, Horn, Shimoni, and Holt, right? CHS, H. So this is the CHSS, so H inequality, okay? I'll send you the link if you want to read this paper, okay? Now, the good news is that we can measure this, and with the scheme that these authors came up with, these experimentalists came up with, you can have a very good measurement of S, okay? So now let's talk more about the experiment. But I want you to understand that violating this is saying that because the proof is done in general, it's kind of in general for a hidden variable theory, you can find that this must be like that. So if quantum mechanics violates this, and you can also prove it, right? Then, um, then we know that in some way, all of these results that we are seeing in quantum systems are not due to our lack of knowledge of, of the system itself, but due to the quantum properties of the system. So quantum mechanics will be, if you can violate this inequality experimentally, it means you are saying quantum mechanics is the right description of nature and is complete. It's not an incomplete theory that is probabilistic because, because we don't know enough about the system. Okay? Does that make sense? I feel like I've talked for a long time without hearing any voices, so I wanna know where we are right now. I understand I mean, this is a complicated matter, but so I understand if you're not following every single thing. I try to do it as clear as possible for people that maybe don't have the background, but that can always fail. So, but what I want you to take now is this idea. This value, this S, can be calculated using a theory that is classical and using quantum mechanics, right? If you use quantum mechanics, then this inequality is violated. So that was the argument from the people that were on the side of Einstein to say, see, quantum mechanics is incomplete. But luckily, we are doing science, which means we can test our theories. So we can have experiments, and this quantity can be measured in an experiment. So if you measure this quantity in an experiment and that quantity violates this inequality, it's a pretty good hint that is telling you that a local theory, a local realistic theory is not possible, and you need quantum mechanics, which has these crazy behaviors that Einstein didn't like something that looked as if a signal was traveling faster than light. So one thing is we can believe whatever we want, but at the end, we can do experiments, and the experiment is going to tell us what can be true and what can not be true. Make sense? Yes, no, a little bit.
For the S,
Yes.
why is the second term negative and all the other terms positive?
Yeah, so I cannot answer that question. This comes in the proof. So if you want to see exactly why that is the case, you have to see the whole proof by CHSH. And I didn't have time to look at that specifically. But the point is that if you define it like this, you can prove that it has to be defined like that. If you put plus, then that's a different quantity. But if you define it like this, that quantity has to follow this inequality for any classical theory. If you want your theory to be local and realistic, it has to follow this. But quantum mechanics violates that inequality. Does that make sense?
Yeah, thank you.
Cool. Kenya, if you have a question, I see you wrote something.
Yeah, I was asking if you had any ideas of what that source could be of that causes the signal or allows the signal to travel faster than the speed of light.
So that's a very good question. There is no signal traveling faster than the speed of light. And I'll try to answer that after we see what the whole experiment is.
Okay.
But actually, maybe I can answer it now. But here, this is the thing. When you look at this quantum state is saying you cannot really think about photon 1 and photon 2 separately. These are part of the same. This is the same system. So it's not like the signal is traveling faster than the speed of light. Is that the system is two parts. There are two parts, and you cannot think about one part without thinking of the other. So therefore, what that means is that measuring one part of the system is measuring the two parts at the same time in some way. So this is how we get around this spooky action at a distance, or this signal traveling faster than the speed of light. States that look like this, if you look at just this state, if you have a quantum state like this state by itself can be divided. I'm going to write this one instead. If you write a state like that, this state is what is called a separable state, or it's a non-entangled state, in which case you can really define the system 1 and system 2 separately. Okay, but when you have a superposition of two of these states, then what you're making is you're making this system be together, and it's going to be entangled, and it's going to be a system as a whole. You cannot really think about the individual parts. So they will be a measurement on one will affect the second. In here, you can have it doesn't matter what you measure here. You're always going to get this state. So it is not this question that you ask, Kenya, is very hard. It's not an easy question to answer, but it's just, you just kind of have to change your mindset into thinking that this is two particles. What you realize is that if you are in this quantum mechanical state, these two particles are no longer two particles, they are just one system. So that's why it is not really that there is a signal. There's not like this part of the system is telling this. No, this is all one system. So let's look at the experiment, how they did this. It's this is just another schematic, but more a little bit more detail than the other one. And this one is because at the end we want to measure the quantity E, right? And to measure the quantity E, we need to be able to measure this type of probabilities, right? I'm going to write it like this. So how do they do that? Well, they have the source that we talk about, and this source emits pairs of photons that are entangled and that are in that state that we saw above. So whenever one is parallel to direction n, the other one is also parallel to direction n. Now, the thing is that it's all very complicated, but this, I didn't mention that, but these states can be written in terms of states that are parallel to A or parallel to B. So you write a bunch of linear combinations there, and that's how you end up getting this value. for the correlation function. But this is just some, let's say, some details of the calculation. We don't care about that at the moment. We just know that the calculation gives you that for that state. Now, we want to be able to measure this, right? Or in some way. And to measure probabilities, what you have to end up finding is kind of relative frequencies, right? And the more measurements you do, the better these relative frequencies are approximated to your probability, right? If you, when you flip a coin, and the coin can be heads or tails, right? The more runs you make, you realize that the probability of tails is 0.5, and the probability, right? You approximate the probability. Theoretically, you know it's 0.5 for each, but when you do it experimentally, you have to do a lot of runs to get it, right? Now, how did they do that then for these probabilities, which had to do the polarization? Well, over here, you have the source. The resolution is not that great, I realize now, but you have the source with the two photons. Here they denoted by their frequencies instead of their wavelengths, but that doesn't matter. You have two different photons with different wavelengths or different frequencies, and you set up a polarizer on each of these cases. But this is not a normal polarizer. Experiments before this will have a traditional polarizer, which is like the one that you have in sunglasses. It blocks the polarization in a given direction. Sorry, it allows polarization only in a given direction, and it blocks the other one. It blocks the perpendicular one. But what they did is they create these filters. So what you have here is that if, when it comes here, the polarization is measured, and if the polarization is parallel to the direction of A, it gets transmitted towards here. But if it's perpendicular to it, it gets reflected. So then you can divide between parallel and perpendicular, right? Now you do the same in the direction B over here. This one, they actually have, because the frequencies are different, they have these two polarizers are not the same. You have to, they make it such that they work for these specific wavelengths. What you do then is you count. These are called photomultipliers. What they do is they count the photons that pass through them, right? So they can detect single photons. The efficiency is not 100%, and that's one of the things that people in support of local theories said that maybe because of that is why they were getting this result and so on. But I'll discuss this at the end. Now, let's assume everything is 100% efficient for now. So what this does is it counts the photons that pass in this direction and the photons that pass in this direction, but at the same time, it counts the coincidences. So if the photon, for example, in a given run, I mean, not a run, because in the run you have a lot of events happening for a couple seconds. I think they do it for about 2 minutes or so. But if for a given pair of electrons, you get parallel here along A and perpendicular here along B, then you see that this tells, this counts the coincidences. So this say, okay, I have an event where A is parallel, where the polarization along A, the polarization is parallel along A and perpendicular along B. And same thing for all of the pairs, right? So you can count the coincidences for every single outcome. Plus, plus, minus, minus, plus, minus, minus, plus, right? So what do? You measure the probabilities, right? So how do you measure these probabilities? Well, actually, here is the correlation function, that how you will do it experimentally. You measure rates. So the first term over here divided by this is the probability, is what you will approximate. I'm gonna just highlight it. Let's just think about this term. This will be the experimental value. I'm gonna put the experiment on the top of this. So this is the rate at which you see they because they have a finite time in which they run the experiment. Then what they do is they find the rate. So they divide by time the amount of coincidences that they got for plus plus, and then you have to divide by the total number of events, right, to get the probability of getting plus plus. Same thing with minus minus, same thing with plus minus and minus plus, right? So if you look at this term will be this whole thing will be the probability of having minus minus, but how you will measure it experimentally, right? Make sense? To measure probabilities like that in the experiment or not? Or is that weird? It's the same as the outcomes on the coin, except you have 4 different outcomes instead of only 2. And these minus come from the definition of the correlation function. So you can measure this quantity experimentally, and then you put it in your equation for S. So you run the experiment 4 different times for different orientations, you can get S. Now, what they did is they even calculated this theoretical value because they're very good experimentalists. So they say, well, the transmission rate, you have transmission rates here, right? Maybe there is a photon that is parallel to A but doesn't get transmitted for some reason, right? This is not 100% effective. So if that happens, the good thing is that that's not going to be counted in this denominator, but still, you have to take that into account, that some events will not be counted. So the transmission rates over here are of the order of 90-something%. They're not perfect. The values are in the specific values of these transmission rates are in the paper. And you see that then, remember, this is the way they write it on the paper. This, what they mean by A comma B is the angle theta AB that we defined before. And what we have is that you have to multiply by all of these in terms of these transmission values for each of the polarizers. I'm not going to get into the details. The details were also not in the paper. I don't know if they have it written somewhere else, but you can calculate this. And this F was also a number that is very close to 1, but not quite 1. And it had to do with the limited solid angle of the photomultipliers, which means that maybe some photons will go away and they will not be measured. So that's why they also have this value of F. Okay, so it's a number here that is close to, this whole thing is a number that is close to 1, but it's not quite 1 when you calculate it. But you can, so theoretically, they say for our setup, this is what the correlation function should be, and experimentally, this is how we measure it. Now, remember, S is equal to this. And what they do is they set up the angles between this A and B prime and A prime to be exactly this. Why do they do that? Because they know that for that angle, they're going to get, theoretically, some people have already proven it, that they will get a maximal value or a maximal discrepancy for this inequality, for Bell's inequality. So that's why they pick those angles. And what do they find? And this is where you see how good at this experiment they were. Well, they find that their theoretical prediction of S is equal to this. So quantum mechanics with the corrections of not having perfect transmission and perfect detectors is going to give you this 2.7 plus or minus 0.05. So remember the maximum value is 2. So definitely a violation of this. And they find that the experimental value is equal to this. I mean, do you see this? Do you see how good they are at this experiment? I bet you have never gotten an error like this in one of your labs. Me neither, by the way. Of course not. So this is very hard to get. So they were very good at this, and that's why this paper had a good audience at the time, and then it made other people come up with experiments to make it even better. And not only they do this, but they have a finite flex, and they show how if they plot this function, right, as a function of the angle theta AB, you see this is the theoretical prediction of quantum mechanics, that dotted line, and these are their experimental points. The error is represented by the size of these points. It's like they have no error in their measurements. It's very small. And you see how they all fall into that prediction between the small error that they have. So this is just giving you confidence that they knew what they were doing, right? So the last things I wanted to mention is that, okay, these people prove this, and you can say, awesome, then quantum mechanics is real, hidden variables theories are completely ruled. But then, you know, there's always people saying, yeah, but what about this, and what about this, and what about this? So more experiments were made so that they couldn't have such arguments. At this point, I feel like maybe there's a few people that say that maybe hidden variables are right, but the debate is kind of won towards quantum mechanics. So for one thing that some people say about this experiment is that you look at the device, the experimental device, so they say, okay, you set the direction of A here and the direction of B here. So in some, and this is all connected. So you say, okay, maybe there is a signal, right, that travels in a slower than the speed of light, right? So it tells this polarizer information about this one, and that's why the things are correlated like this, and so on and so forth. Well, some people say, okay, well, what we're going to do is then we're going to pick the direction of these two polarizers randomly. They already did that, and they separated the two polarizers by, I want to say, how many meters? I think it was around, well, it was a distance enough that because of how fast they were changing one polarizer and then the other, that if they were communicating between each other by some way that they didn't know, that would have to be faster than the speed of light, right? So it was already, so it rules out, let's say, that loophole. And so on and so forth. There is another one that they did 1.3 kilometers, almost a mile difference, and they still find this violation that is predicted by quantum mechanics. So yeah, the experiments have become more advanced and harder to, because the technology on the photomultipliers increases. Now you have a better detection efficiency and so on, and you can come up with these new setups. So yes, as the technology has increased, then the experiments can be made more ideal. And what we know now is that pretty much the hidden variable theories are ruled out. So Einstein was wrong. Some there might be some arguments that still rule for those, but at some point we have to pick the theory that is the simplest one, right? So it's like, you see, all of this can be explained with quantum mechanics. It is explained perfectly. So why do we have to come up with another theory that you have to go around and pick and imagine that you have these hidden variables and so on to describe nature? So Occam's razor picks quantum mechanics as well. And that's all I had to share today. I will send you the links actually before we go, but let me know if you have any questions. I had a lot of fun preparing this. I hope you had some fun too.
If anyone has questions, you can unmute yourself, or you can share them in the chat. Or if you just have, I guess, points you found particularly interesting or that are over your head, now's your time.
Yeah.
So
Yes. I'm gonna send you a bunch of links that you can click on if you want. That's the original paper.
perfect.
This is the original Epr paper from 1935. That's a little bit hard to understand, to be honest. But if you're interested, you can go ahead and look it up. Then it's Bell's original paper. This one is already the PDF because it was published in a magazine, in a journal that died very fast, so it doesn't exist anymore. But CERN, he was a scientist at CERN, and CERN has it in their web for free. That's the generalized inequalities. Give me 1 second for the questions. I just want to send all of this information. This was the one that was done in 1988, but some Austrian scientists in Innsbruck. The one that they started doing the random direction of the two polarizers so that nobody could say that they were communicating. And the last one I saw was in Nature. It says loophole-free Bell inequality violation using electron spin separated by 1.3 kilometers. Where was this done? I forgot. I want to see the what is it? The affiliations of the authors, but yeah, I will send you that as well. It's a whole world to explore. It's very fun. Okay, I see. Okay, no, there's no questions. Just Brenda said that it was interesting, and thank you. Okay.
Yeah, I don't. No questions. Okay. Okay.
You know if
All right.
CERN is still doing research related to this topic?
Sorry?
You know if CERN is still doing research related to this topic?
No, CERN is not doing research related to this topic, and this person was working in high energy physics, Bill, and he just decided to write a paper on his thoughts on. Some like a side gig basically, and it turned out to be the most important thing that he did. So yeah. But yeah, all right. It was a pleasure being here. I hope you had as much fun as I did.
Yes, thank you for. Bye.
Yeah.
Thank you so much
No
for
problem.
presenting.
Thank you so much.
Bye. Take care, everyone.